Let's look at two confidence interval examples. Number one, many people eat frozen meals for lunch, but how many calories do these meals typically contain? In order to estimate the mean calorie content in these meals, a random sample of 46 meals were examined for their calories. The 46 meals produced a mean of 382 calories with a standard deviation of 63 calories. Provide the desired estimate to the nearest tenth of a calorie using 95% confidence. So what we need are the sample mean, the sample standard deviation, the sample size, and the t-critical point. So y bar is 382 calories, the mean from the sample. S is 63 calories, the standard deviation from the sample. And we know there were 46 meals examined. Now the t-score would come from table T. So 2.014 is the value, but how do we find that? Remember, we want 95% confidence, and the degrees of freedom would be 46 minus 1, or 45. So this table T, and remember, you have one-tail probabilities, which is only the area to the right of the number in the table, and you have two-tail probabilities. The two-tail probabilities are going to give you the area in red as the alpha value, or the two-tail probability. So 1 minus that would be your level of confidence. Since we want 95% confidence, we want to be in this middle column, okay, where you've got 0.05 as the two-tail probability. That leaves 95% in the middle for the level of confidence. Now remember, our degrees of freedom were 45. So at 45, the row for 45, we get 2.014 as the t-score. So 2.014. Next, we write down our formula, y bar plus or minus t sub df times s over the square root of n. Substitute your numbers, 382 plus or minus 2.014 times 63 divided by the square root of 46 equals 382 plus or minus the margin of error of 18.707730. So that rounds off to 363.3 for the lower limit and 400.7 for the upper limit. So now we want to summarize our findings by interpreting that interval. So in conclusion, I would say I am 95% confident that the mean number of calories in all frozen meals is between 363.3 calories and 400.7 calories. Now the interval is valid. How do I know that? Well, a random sample of 46 meals was collected where the number of calories in each meal was recorded. So I have a random sample of quantitative data. Sigma is not known, so the sample standard deviation of S equal to 63 calories is used. And then the sample size, n equal to 46, is at least 30, so I have a sufficiently large sample size. Now look at example 2. A police force is considering a brand of cars for a new fleet for officers. The purchase cost is known, but the operating costs are unknown. A random sample of 41 cars of this brand is obtained and driven by officers for 10,000 miles. The operating cost in cents per mile are carefully recorded. The mean is found to be 11.6 cents per mile with a standard deviation of 0.95 cents or cent per mile. Use this information to provide an estimate of the mean operating cost for this brand of cars in which you have 90% confidence. So again, we need the sample mean, the sample standard deviation, the sample size, and the t-critical point, which will be based on df equal to 41 minus 1, or 40 degrees of freedom, and we want 90% confidence. So that would be 10%, or 0.10, as the two-tail probability. So the sample mean is 11.6 cents per mile. The sample standard deviation is 0.95 cent per mile. The sample size was 41, and the t-score actually turns out to be 1.684. Where does that number come from? Let's look in table T at 40 degrees of freedom and the 0.10 two-tail probability, which is your 90% confidence column. So two-tail probability 0.10, so we're in this column, and we wanted how many degrees of freedom? 40. So our score is 1.684. Okay, back to our example. So what would come next? Writing the formula and plugging in your values. So y bar plus or minus the t-critical point times s divided by the square root of n equals, substitute, 11.6 plus or minus 1.684 times 0.95 divided by the square root of 41, which equals 11.6 plus or minus 0.249847, which is your margin of error. So that gives, when rounded, 11.35 to 11.85 for your estimate of the population mean mu. Now let's write a sentence to interpret the interval. I am 90% confident that the mean operating cost for all cars of this brand when driven by police officers is between 11.35 cents per mile and 11.85 cents per mile. Finally, is this valid? Yes, the interval is valid. We have a random sample of 41 vehicles which were driven, and the operating cost in cents per mile were recorded, so it's quantitative data. Sigma is unknown, so the sample standard deviation of S equal to 0.95 cent per mile is used, and the sample size, N equal to 41, is at least 30. So there's a sufficiently large sample size.